In this video, we will introduce our work, DyBluRF, Dynamic Neural Radiance Fields from Blurry Monocular Video. In real-life video captures of dynamic scenarios, extended camera exposure time often introduces motion blur. If objects in the scene move or the camera moves during the exposure time, the moving objects or the background in the captured image will appear motion blurred. Recent advancements in dynamic neural radiance field methods have yielded remarkable outcomes. However, these approaches rely on the assumption of sharp input images. When faced with motion blur, existing dynamic NeRF methods often struggle to generate high-quality novel views. Recently, some NeRF-based methods have emerged to tackle the motion deblurring of static scenes. However, these methods cannot address blurring caused by object motion and cannot effectively represent dynamic scenes. In this work, we aim to input a monocular video with significant motion blur in a dynamic scene and recover a sharp dynamic neural radiance field to obtain sharp novel views of the dynamic scene while maintaining spatial-temporal consistency. In this paper, we adopt a separate representation for dynamic and static components which prior arts have demonstrated the superiority of this method in handling large scene motion, where motion blur often occurs. Subsequently, we output the dynamic, static, and fusion results, and obtain the predicted RGB images through volume rendering. To handle input motion blur, we also model camera motion within the exposure time. We divide one exposure time into many timestamps for separate representation. In this way, we can obtain the predicted sharp images for each timestamp after the volume rendering. Finally, we average the images within one exposure time to obtain the predicted blurred image and calculate RGB loss with inputs. Although the above pipeline can represent dynamic scenes from motion blurred input, it may inadequately capture the temporal consistency in dynamic scenes. To mitigate this issue, we make the dynamic model additionally output DCT coefficients to express the motion trajectory of scene spatial points. We also introduce data-driven priors to constrain the scene geometry. To overcome the inaccurate depth or optical flow caused by blurry input images, we propose extreme value constraints to make the model learn accurate scene representation. Since there is a lack of datasets specifically designed for addressing motion blur in dynamic neural radiance fields, we have curated a collection of dynamic scenes with motion blur from an existing stereo blur dataset. Here are the visual comparisons with existing dynamic NeRF methods on the dataset. Notably, existing dynamic NeRF methods cannot handle motion blur inputs, resulting in low-quality novel views in both dynamic and static regions. In contrast, our method can effectively manage inputs with motion blur and produce sharp and high-quality novel views. Furthermore, to demonstrate the superiority of our method in modeling motion blur in 3D space, we first pre-process the input blurry images with 2D deblurring and then train dynamic NeRF models. Results show that our method continues to outperform the alternatives. Thanks to the timestamps modeling in exposure time, our method can obtain a temporally interpolated sharp video from the input blurry video. Also, because of the EVC constraints, our method can restore sharp depth map from the input blurry depth. Thank you for watching.